Vanakkam. Today is a very interesting topic. As human beings started evolving along with the apes, they found that they were at a great disadvantage. They couldn't run fast like the cheetah or the tiger and catch a prey. And even if they did get a prey, they couldn't tear the animal with claws or teeth. So, how were they going to survive? This is where two important aspects came in: the brain, which was growing bigger and bigger, and the hand, which was developing skills. Skills to create tools, to make tools, to catch the animal and to kill it. Essentially, two processes: throwing and clubbing. But of course, the hand must go through a lot of changes to allow all these extra movements to come in. The movements that we use day in and day out today. How did they develop? What were the changes that occurred in the hand? How did we differ from our cousins, the apes? All this in this interesting video on the evolution of the human hand. When we start to study about the evolution of the human hand, we will need to study about the discovery of fossil hand bones of our human ancestor Homo habilis alongside core tools at Olduvai Gorge in the early 1960s. This gorge is present in Tanzania, where the bones of the species resemble our hand bones. Since then, the evolution of the human hand has been a source of great speculation and debate. Many theories have existed as to how and why the hand had evolved. But there is one plausible theory: the role and the use of tools in our early ancestral culture, which has led in a big way to the evolution of the hand as it is now. So, as the brain capacity increased, the species started using tools. This revolutionized the development of the human hand in many ways. So in this video we shall see what changes have taken place in the hand, how these changes have happened, and how this remodeling of the human hand was made possible by the reproductive advantages that it allowed. This is an artist's depiction of the Homo habilis, and the name represents able or handy or mentally skillful. The hand in this species showed 5 main changes: opposability of the thumb, complexity of the carpal bones, asymmetry of the hand, rotation aids that started developing in the hand, and a shortened hand. The primary and most important change is the opposability and the length of the thumb. Now, opposability is a common trait that is seen in all the great apes, that is, humans, chimpanzees, bonobo monkeys, orangutan, and the gorilla. And opposability of the thumb to the fingertips of all the fingers on the same hand is seen in all these great apes. And you can see the changes in the length and the shape of the first metacarpal bone or the thumb metacarpal bone in all these species in order. But ultimately the human thumb became very unique because it had the ability to cup and grip items firmly in order to manipulate them. It showed greater mobility in comparison to the other primates. There were larger muscles and more number of muscles, and it was much longer in comparison with the thumb of other primates. This powerful thumb opposition seems to have appeared around 2 million years ago, and this correlates in time with the archaeological evidence for an increased reliance on stone and bone tool use and animal butchery. Humans and Neanderthals, the so-called Stone Age men, showed powerful thumb opposability, that is, they had a high biomechanical efficiency, and this was due to large opponens pollicis muscles and flared muscle markings. The grips of the chimpanzee differ profoundly from those of humans, because they use it for suspension from horizontal supports, and it is mainly the use of a hook grip of 4 flexed fingers. With vertical supports, a diagonal hook grip is used. The thumb may touch the support but does not squeeze it against the palm. Chimpanzees use this grip when flailing with sticks, but when the arm swings forward, the hand tends to lose its grip, possibly due to weakness of the thumb and its inability to overlap the index finger. Because the thumb is weak and short, its distal phalanx is relatively immobile and its distal pad cannot be opposed to those of the fingers, so it cannot generate a firm pinch or squeeze. Whereas the human thumb metacarpal articulates with the carpals in a saddle joint. This, when combined with remodeling in the metacarpal phalangeal joint, and the distal pad can be placed against those of the other fingers, providing full opposability. And this is what makes the human thumb unique as far as opposability of the thumb is concerned. The second important change that has been noted in the human hand is the complexity in carpal bones when compared to the other great apes. In the modern human wrist, there exist many complexities. For the purpose of grasping for tool making, there are two aspects of the wrist that are specially significant. The first point is that the base of the second metacarpal has become extremely complex, allowing connectivity to 3 carpal bones, the trapezium, trapezoid and the capitate, and this makes the second metacarpal very stable and also maneuverable. The second important point is that the broadness of the trapezoid and capitate work to relieve the stresses that form due to the opposition of the thumb to the fingers during manipulation. Along with the changes in the complexity of the wrist came a marked asymmetry on the hand. This was brought about by the distinct shapes of the second and fifth metacarpal heads. These heads are asymmetrical to each other and have distinct projections on the outer areas. It enables these fingers to rotate towards each other during flexion of the fingers. This reciprocal motion permits the hand to form itself around an item and grip more firmly for manipulation. This slowly got combined with what were known as rotation aids, a unique saddle joint developed between the fifth metacarpal base and the hamate bone. This was what contributed to the reciprocal rotation between the second and fifth metacarpals. As a result, there was an increase in the overall strength and precision of the grip and the range of overall dexterity. And also, when the fingers are flexed, they rotate towards the central axis so that the fingers can meet the tip of the thumb. So effectively, what has happened in the human hand is that the metacarpal hamate articulation permits supination of the fourth and fifth metacarpals, and the heads of the second and third metacarpals allow pronation of the proximal phalanges of the index and middle fingers. As all these changes occurred, the hand also became shorter and developed many other changes in the fingertips and the palm. When we compare the chimpanzee hand and the human hand, we find many striking differences. The typical primate hand has a diminutive thumb in combination with long curved fingers, whereas the human hand has larger, more muscular and fully opposable thumb combined with fingers that have shortened and straightened. Obviously, this striking difference is the result of evolution. This shortening of the human hand provides greater stability and better stress endurance. The distal phalanges have gained large apical tufts which support broad palmar fibrofatty pads that distribute pressure during forceful grasping and whose deformation accommodates the pads to uneven surfaces. We have seen that the evolved human hand had a longer thumb, but along with that, the intrinsic thumb muscles are larger and three new muscles add strength and control to thumb movements. The flexor pollicis longus muscle, which is absent in chimpanzees, the deep head of the flexor pollicis brevis, and the first volar interosseous muscle. Because the fourth and fifth metacarpals are progressively shorter than the third, there is an obliquity to the hand when the fingers are flexed. This produces flexure creases that run obliquely from the lower ulnar side of the palm to the upper radial side. The thenar and hypothenar eminences are enlarged by fat pads which overlie the corresponding muscles. Contraction of the palmaris brevis muscle stiffens the hypothenar pad. The stability of the third metacarpal base is enhanced by a styloid process on its dorsal radial aspect. When the finger is extended, the styloid process locks the carpal and metacarpal bones together, preventing hyperextension. Also, a ligament developed from the pisiform bone to the bases of the third to fifth metacarpals, further restraining hyperextension. So we have seen some of the changes that occurred in the human hand with evolution. But what did all these changes do? It had what is known as an adaptive significance according to Napier, who described it in 1965. According to him, the human hand gained two new grips. In his own words, there are only two prehensile actions. These are called the precision grip and the power grip. The precision grip is employed where precision of movement is required, and the power grip is used for application of force. So according to him, precision grip is a throwing grip and the power grip is a clubbing grip. What this throwing and clubbing are, we shall see later on in this video. These two patterns of grip are anatomically and physiologically distinct and provide the basis for all prehensile activities. Napier went on to illustrate the two grips with photographs of hands grasping a ball and a cylindrical rod. His analysis showed that the human hand is adapted for gripping spheres and cylinders. In Napier's description of the precision grip, the terminal pad of the thumb forms one jaw of a clamp, the other being formed by the fingertip pads. When large objects are held in this way, they involve all the fingers, but smaller objects require only the thumb, index and middle fingers, with the fourth and fifth fingers providing lateral stability. This is also called the three-jaw chuck grip. This grip was originally used for throwing objects. If the object is thrown, the fingers contribute to the aim, the propulsion and the velocity. By contrast, in the power grip, the clamp around the cylinder is formed by the partially flexed fingers and the palm, counter pressure being applied by the thumb, which is wrapped over the dorsum of the fingers, where it acts as a buttress to reinforce the grip. It is also called the finger active palm squeeze grip. It employs all the fingers to secure a cylindrical tool against the palm so that the tool functions as an extension of the hand and forearm. So far, we have seen the anatomical changes that occurred in the human hand with evolution and the grips that started developing in this evolved hand. But how are the two connected? They are related to the two movements of throwing and clubbing. Other animals could run fast and catch their prey for food. But the newly developing species of the humans could not do so because of their bipedal gait. However, they needed to protect themselves from bigger animals and they also needed to hunt for prey. So they had to learn to throw tools that they developed like stones or spears to catch their prey. For efficient throwing, the hand must be able to grip the missile while energy is transmitted to it and then accurately control its release. This requires a fingertip grip, as we have already seen. The thumb must be long enough and sufficiently mobile to oppose its fingertip pad to the missile on one side, while the fingers oppose their distal pads to the opposite side and adjust themselves to irregularities in the naturally occurring rock spheroids. For accurate release, the fingers must be under precise neural control and also able to absorb without injury the reaction force resulting from the propulsive thrust. This was possible because we have seen that the thumb has lengthened and can be fully opposed to the fingers, which have shortened. The thumb and the first two fingers, which play the major role in this throwing grip or the precision grip, are strong and robust. Thumb opposition is enhanced by addition of a muscle that flexes the terminal phalanx and is matched by rotation of the fingers as they flex, that is, supination on the ulnar side and pronation on the radial side, exactly as needed for a fingertip grip of a sphere. Broad apical phalangeal tufts support soft fleshy fingertip pads that adapt themselves to irregular spheroids and provide a large friction surface. The fingertips are highly innervated with sensory endings that inform the brain about the missile that is being held and the forces acting on it. Precise neuromotor control of finger muscles permits sub-millisecond release times needed for throwing accuracy. When a missile is released, there is only one point on the arc of the moving hand where release will result in movement towards the target. Abduction of the thumb and extension of the finger joints control this action and must occur at the correct point of time. A 1 millisecond delay in finger extension causes a change in direction of 2.2 degrees. Enhanced control of the hand, a key element in throwing accuracy, is reflected in expanded representation of the fingers in the human sensory and motor cortex. As the missile is thrown, kinetic energy that is transferred to the missile is channeled through the index and middle fingers of the throwing hand. At release, the thumb drops away, these fingers extend, and their apical tips provide the final thrust. An equal and opposite reaction force acts to hyperextend these fingers, particularly the third finger, which due to its length is the last to lose contact with the missile. Stress travels down the phalanges through the metacarpals in the palm to the carpal bones where it is dissipated. The robustness of the second and third fingers, which absorb stress, the styloid process, and the ligamentous stabilization of the third metacarpal prevent hyperextension. This throwing action of the hand can help the man to catch the prey, but he did not have teeth like the other animals or claws to kill the prey and tear open the prey. So the next movement of clubbing developed, where he had to use force to kill the animal or tear it open. Effective clubbing requires a secure grip, especially during the impact, so that the time during which the force is applied is maximized, diversion of energy into elastic recoil is minimized, and the clubber may use the weapon again immediately. Fingers and thumb form a vise, squeezing the club handle against the palm. And for added force and grip strength, both hands may be used. Several features that contribute to the throwing grip also facilitate the clubbing grip. Supination of the fourth and fifth fingers during flexion aids the grip of a large spheroid and acts to apply the palmar force of these fingers to a club handle oriented obliquely across the palm. Distensible fingertip pads, which maximize surface contact with spheroids, perform the same function on club handles. A longer, fully opposable thumb, essential for the throwing grip, also facilitates gripping a club by enabling the thumb to overlap the ends of the index and middle fingers. The flexor pollicis longus muscle is effective in both grips. Other adaptations are specific to the clubbing grip. One of these is the slant of the metacarpal phalangeal articulations. When the fingers are partially flexed, they form an oblique line. Together with the partially flexed thumb, a corridor is formed, that is, a cylindrical cavity lying diagonally across the palm. When a club is squeezed against the palm, this anatomical configuration assures that it is positioned in an oblique manner. On the ulnar side, the implement is clamped against the hypothenar fat pad, stiffened by contraction of the palmaris brevis muscle, while the thenar musculature and its subcutaneous fat layer buttress the radial side. When the club is swung, the wrist deviates in the ulnar direction just before impact. Combined with the oblique angle of the grip, this aligns the club with the forearm, increasing the radius of arm plus club and the velocity of the club, thereby providing maximal mechanical advantage. At impact, the reaction force acts to drive the club in a direction opposite to its former trajectory. The base of the handle exerts pressure on the base of the fingers on the ulnar side of the hand, whereas the apical end of the handle is driven against the radial side. If the grip is to be maintained, these two parts of the hand must be capable of withstanding the stress of impact. On the ulnar side, the base of the fifth finger absorbs much of the impact. Its metacarpal has thickened and its base has enlarged. The thumb stabilizes the club handle on the radial side. Modified carpal bones on the radial side help to dissipate stresses generated in the thumb during clubbing. A group of chimpanzee-like apes began to throw rocks and swing clubs at adversaries, and this behavior yielded reproductive advantages for millions of years, driving natural selection for improved throwing and clubbing prowess. I hope you liked the video. I enjoyed making it. Please do click on the shown links to see more about the embryology and the classification of congenital hand differences. And do not forget to subscribe to stay connected with the latest in learning hand surgery, plastic surgery, trauma surgery and ethics. Vanakkam.